So the first part is history of specular gloss. I will be quite short on this, but before going to actual and state of the art in terms of specular gloss measurement, it's good to know where we come from. So I will try to summarize a little the progress on how we ended up with this ISO 2813 and everything. In fact, all this work is there to measure gloss, so maybe the best is to ask ourselves, as they did at the beginning of the 20th century, what is gloss? And so if you go to the definition given by CIE, you know that gloss is the mode of appearance by which the reflected highlights of objects are perceived as superimposed on the surface due to the directionally selective properties of that surface. This is an example that illustrates a gloss scale from the left to the right with an increasing level of gloss. So you see that the highlights of the object are getting more and more clear, and this is a sign that the gloss is increasing. But what is important is to notice that the three first words of the definition is mode of appearance. It means that gloss is a sensation, a visual sensation, and if we want to build a measurement, we need to find a numerical value that correlates with that sensation. So that's what they did, in fact, when they started to try to develop gloss meters. And if you want to make a measurement of a sensation, you have to ask observers to what is this sensation. So if you ask to an observer to evaluate the gloss of an object, for instance, here I have a glossy object, what the observer will do is that he will look at a light source, and then he will put his look in the specular direction according to the surface, which is exactly in this direction here on my slide. But what you will notice also each time you will make an attempt is that the observer doesn't stay immobile in the specular direction, but it rotates a little the samples in order to evaluate the evolution of the directional reflectance around the specular direction. And if you ask your observer to not move the sample, then you will see him moving his head in order to catch as well the value of the reflectance in and around the specular direction. So if we go on all the bidirectional reflectance distribution on a surface, if you want to fully characterize the optical properties of the material, in fact, what you will notice is that the information concerning gloss is here, exactly in the specular direction and around the specular direction. And this particular area of the bidirectional reflectance distribution function, the BRDF, is what we call the specular peak, the region where the light, you collect the light that is reflected only by the surface. It's not the part of the light that will create the color, which is the light that will cross the surface and interact with the pigment. It's the light that is reflected only by the surface. Then, if you look at this specular peak, what you see is if the surface has a low roughness, or even let's say if the surface is perfectly flat, then you will have all the light that is reflected by the surface that will go in the specular direction. If you put a small roughness, then you will have a peak that is very peaky and very sharp, in fact. And usually, if you have a surface that has a low roughness, it's a glossy surface. Now, if you go on a more medium roughness, then the light here will hit different orientation of that roughness and then will be reflected in a direction that is not only the specular. And you will see your peak getting larger, but also smaller at the same time, because the amount of light, the integral you have here, is almost constant. This is a less glossy surface. This is a satin surface because the roughness has increased. And if you go on a very rough surface, then you will not see a specular peak, in fact, because the flux is reflected almost in any directions, and you are in front of a matte surface. That's mainly the relation you have between the sensation of gloss, the specular peak, and the looseness that is linked also to the gloss. So that's the observation you can do. That's the observation that people have done, researchers have done at the beginning of the 20th century. And now the idea is to measure it. If we put the field stop here around the specular direction, then we will select one part of only the part of the light that is in and around the specular. And according to the field stop, the size of the field stop, you can really get, if you measure the light that is after the field stop, you will have an indication of the gloss, in fact, because here it's very glossy. All the light goes through the aperture because the peak is sharp. So you have a high signal for a high gloss. If here you will collect less light because a little of that light is not in the specular, it will be stopped by the field stop. And so the signal after, if you collect the flux, will decrease. It's good because the gloss is decreasing. And if you go on a matte surface, then you will have a very small signal because most of the light will be out of the solid angle that is going inside the diaphragm or the field stop. So if you do something like this, you get a numerical indication that is proportional to the sensation of gloss. You're building a gloss meter. So 1914, this is what is called the first gloss meter. It's called, at that time, the publication, it's a glarimeter. It has been developed by Ingersoll, and it's really made for the measurement of the gloss of paper, because there was a strong industrial need at that time to characterize the gloss of paper. So this device is a 45-45 geometry. You have the light source here, you have the sample here, and then you will look at the light reflected in the specular direction. And what Ingersoll says is that it compares the light reflected in the specular direction with the light reflected by a perfect diffuser. That's the first effort. But in fact, the researcher that really has been important in this field is this gentleman. So it's Richard Hunter from NIST. And I really think that this is the person who brings to us the gloss meter and the standards that we have today. The approach of Hunter is really interesting because he is a metrologist, but he has also spent a lot of time trying to doing psychophysical studies, evaluated the visual sensation, but always with a look of metrology. So trying to put scale, trying to put uncertainty on the scales. And this is a very interesting approach, an approach that I really support, in fact, in my work today. So Hunter will do a lot of psychophysical experiment, and then he will show first that gloss is not unique. You can't get it only with one number. It depends on the type of gloss, and he identifies 6 types of gloss. And the one we will measure with the gloss meter is one of those 6 types, which is the specular gloss. Then he also worked a lot on the size of the apertures, and he noticed that 45 degree is not the geometries that gives the best sensitivity. It's better to work at 60 degree. So that was also a major publication. And finally, this part I'm not completely sure, but I couldn't really find it in my books. But in fact, it's at that time that we moved from the comparison with a perfect diffuser to a comparison of the flux according to a standard black glass. So Hunter will really also participated in the ASTM work and will be one of the major contributors to the D523, which is the standard that has given the ISO 2813 that we are using today. What do we have in the D523? We have this geometry 60 degree. It's published in the first version, is published in 1939. The rectangular aperture is quite large. In fact, it's 4, so it's rectangular, and it's in the angle is larger in the azimuthal direction rather than in the zenithal direction. It's put like this. In fact, if you look at the sample, if it's horizontal, and the value of gloss is given by 100 times the flux reflected by the sample divided by the flux reflected by the standard, and the standard is a black glass with a refractive index of 1.567. And then we had the revision of this ASTM D523 that comes several years later, where they added other geometries. We are quite late. I will not spend too much time on this. It's just that if you have a matte sample at 60 degrees, you have very low flux. What you will notice is if you increase the zenithal angle on the matte surface, then you can see appearing a specular peak because of the fact that first you have the Fresnel factor that increase, and second, the appearance smoothness when you look at the surface at a grazing angle is smaller than when you look at normal. So for that reason, you see a peak, and then you will get a more sensitive measurement if you move at 85 degrees with your illumination. That's why they developed this, and they did exactly the opposite for very high glossy surfaces. Then it's better because the peak is very sharp here. It's better to try to enlarge the peak, and you get it if you decrease the zenithal angle. This is the 20 geometries that has been added during that revision. And we are still there, in fact, in terms of geometry, in terms of apertures, nothing has changed since 51. The things that have changed is the realization of the standards, because the D523 specifies that the primary standard is a glass surface having a refractive index of 1.5.6. It's not said explicitly at which wavelength, which is a bit pity, because in fact we will see that we are talking about a broadband system. So a broadband system can't have a constant refractive index, whatever is the wavelength. So that's why when when the ISO 2813 has been developed based on the ASTM standard, they specified that this refractive index is taken at the sodium D line. The standard proposed by EMPIR was a black glass, so a refractive index of 1.52, and you need to do a correction, of course. But in fact, in the 80s, Boude from NRC complained a bit about that standard because it was not strong enough. It was getting scratched. It was getting polluted easily. And so he proposed to use a fused quartz. And he put an edge because the quartz can't get black. So then if it's transparent, you will get the reflection on the backside of the sample in the direction of the measurement, which is, of course, not good. So, but if you put an edge, then that second reflection is going out of the direction, and you're good. And then later in 2000, Maria Nadal and Thompson proposed to use BAK50, and Clarence will talk about it, I guess, later. This is the same quality of the quartz edge, but in fact, you have a refractive index that is almost the one of the standard, so the correction is getting lower. And we are here. That's almost all for the story. Now it's the present time. We have this ISO 2813. This is the fourth revision. Last one has been done in 2014. And it's maintained by Dean in the TC 35. This is the design that you will find in the standard. So it's a quite simple system. You have a light source. You put here a field that will be the entrance of the system at the focal of a lens. Then you get a collimated beam. You have to manage, of course, the direction of illumination at 60, 20, 85, whatever. Then you have the sample. The sample reflects the light. You go only in the specular direction. And then you have here a lens. And at the focal area of the lens, you get the image. So this part is conjugated with that part, of course. So you get the image of the source aperture here. But you put also a second rectangular aperture that is defined by the standard to collect the light not only in the specular, but also around the specular. And that's this information that will give you the different values according to the gloss. Few details. Interesting on the light source. The recommendation is an illuminant C. And I'm sure you know quite well D55 illuminant A, but the C, I'm not sure. It's normal, but it's not very used, but it's used at least in the gloss meter. So this is average daylight at a without the UV, but at color temperature very high, so 6,700. And so this is the C illuminant here, so there is no UV. It's very close to the D55, in fact. And what I noticed is that in commercial instruments, this parameter is not really well respected in a lot of gloss meters. But in fact, it's not that important because gloss is not really sensitive to color, to the color of the sample. So it will have, in fact, the spectrum of the light source. On the detection, this is a v-lambda spectral sensitivity that you have to develop. That means that you need to put here a filter that will have spectral mismatch factor adapted to the illuminant or whatever. That's the only thing that is difficult. And then you have also to control well your aperture. It's almost all. The field, they are defined in the standard. So this is the field, the illumination aperture. Here it's 0.75 degree by 2.5, and for the detection, it depends on the angle. For the 60 degree, which is the larger, it's a very large, in fact, aperture. It's 11.7 degree in the zenithal plane, which is huge. You collect almost everything. Where for 20, because it's devoted to high gloss surfaces, it's smaller, and for 85, it's also smaller. Particularly, it's because the size of the peak will really decrease when you increase the zenithal angle. The standard says that at 20 degree, it's for high gloss surfaces, 60 semi-gloss and 85 matte surfaces, but I'm pretty sure that you don't know exactly where the border is between matte and semi-gloss or between semi-gloss and high gloss. So what people have to do, in fact, is you take your sample and you measure it at 60 with the 60 geometry. And if you get a gloss value higher than 70, then it's better to use the 20 geometry. If you get a gloss value lower than 10, then it's better to go to the 85 geometry because you have a very matte sample. There is no correlation between the scales. That means that each time you do a measurement, you have to indicate the geometries that has been used. Otherwise, you lose completely the traceability, in fact. And one thing that is said in the standard is that gloss value measured on coatings are expressed rounded to the nearest integer. So you're not supposed to put a decimal here after your measurement, even if sometimes some gloss meter provide it. So it could be, a result could be something like this. For instance, you specify the geometry, gloss unit in capitals. And this is an example, for instance, on 6 different samples. And you see that it's pretty convincing. If you have a low gloss value, it's a matte sample. If you have a high gloss value, it looks glossy. So we can say that this thing works. In fact, the correlation between the gloss and the visual sensation is quite good. There has been several studies, and they all give the same thing. It's good, particularly at the middle of the scale. then when you go on in the mat, it's not the same criterion, and you see that the sensitivity of the gloss meter is very poor according to the sensitivity of the visual system that is here plotted in ordinates. And it's also not really good in the high gloss, and for other reasons, but we are late, so I'm not going to develop this now. And that's all for me. Thank you for your attention.